Okay, so we just continue on. Um, so let's apply what we just have here. So we have A forward over A reverse is the exponent of delta S over R, and E forward minus E reverse is delta H reaction. Okay, and so you can see now what I was talking about yesterday in terms of Gibbs free energy and kinetics, and the rate of my reaction crossing the room. Okay? So the frequency at which I cross the room depends on my change in entropy, right? And the enthalpy change depends on whatever barrier is in my way. Okay? So you can see how they're interconnected. All right. So for the reaction, trans to cis perfluorobutene, the measured rate constant forward direction is 3.16 times 10 to the 13 times the exponent of minus 31,030 Kelvin all over T. Okay? So we have an activation temperature. Given that the enthalpy change for a reaction is 342 kilojoules per mole, and the entropy change is minus 2.03 joules per degree Kelvin per mole, calculate the reverse rate constant at 750 Kelvin. So we know that A forward over A reverse is the exponent of delta S over R. So we have A reverse is equal to A forward times the exponent of minus delta S over R. And you're given delta S, so you can get A reverse. Okay? I actually should have it written here. I don't, but you can calculate that yourself. Okay? So for some homework tonight, do that, and you can tell me tomorrow what A reverse is. Okay? Check with your friends. Okay? And you have E forward minus E reverse is equal to delta H. So E reverse is equal to E forward minus delta H. Okay? And just be careful that you convert this activation temperature to an activation energy, and that you have the energies in the same units. So it's not T, it's joules, and it's joules, not kilojoules, or kilojoules and not joules, or whatever it is. Okay? Just watch that. Okay. Okay, so here's a reaction profile diagram. Okay? And we have here, if you wouldn't mind just maybe writing it on your notes, you could write here underneath NC3H7, for example. Just to give you some example. N-propyl, NC3H7. And here you can write C2H4 plus CH3. Okay. So this would be a reaction coordinate diagram for that reaction. Okay? And so here we have, a line here depicted. Here we have going up here, and then arriving here at products. Okay? So here we have reactants, here we have products. Okay. So what's on the y-axis? Well, it's an energy, typically Gibbs free energy. Okay? We have an energy. And on the x-axis, it's what we call the reaction product identity, or the reaction coordinate. Okay? So so you've written here, right? You've written here NC3H7, and you've C2H4 plus CH3 here. So what's happening? So we have this reaction, right? 1, 2, 3. Okay? And what's happening? We're going to get okay? So the electron here is going to move in, and this is going to move out here. We're going to break this bond, and we're going to produce methyl radical and ethylene. Okay. So, but how does that happen? So how does this bond break, and we get ethylene plus methyl? How does that happen? Okay. So what happens is the this carbon starts to move away from the other carbon. As it moves away, what happens? Yeah, there's a resistance. Okay, so you've got this model, what is it, the spring, the Hooke's law sort of thing, the spring model. And so there's a resistance, and the carbon-carbon bond tries to maintain itself. Okay, so we have to put more and more energy into, as we pull them apart, we have to put more and more energy into it to get them to break. Okay, and we eventually reach this point where you're just on the cusp of breaking it. Okay, and then all of a sudden the spring breaks. Okay, and then everything relaxes back down to the products. We get ethylene and methyl radical. The radical settles on the methyl group, and we have ethylene. Okay, and so this is the reaction coordinate diagram for that process. So each point along this line is the widening of the bond, or the stretching of the bond between the two carbon atoms in the molecule, and the increase of energy of that process. Okay? Okay, so here I have just an example again. So I've described it now, but here's a picture of it. So here we have dimethyl ketone, so acetone, undergoing H atom abstraction by OH. Okay, so there is some complex at the start here. I'm not going to go into that, okay? But that's why this is situated where it is. If the hydrogen atom is attracted to that oxygen atom and the carbonyl, okay? But we have the OH sitting up here, and it's going to abstract this hydrogen atom. Okay, and if we play that, you can see here's the reaction coordinate, here's the energy. And if we watch it here, it's relaxing back now to the products, which is water and the radical. Okay, so I'll play that again. Okay, so you can just watch it and see. Okay, so the hydrogen atom is getting close. Now it breaks and it's attracted to the water. And so the breaking point is just at the tip here. Okay, and then everything relaxes to the products. I chose this one because this is actually an exothermic reaction. So if we go back here, this is endothermic. Okay, we have to put ultimately this amount of energy in to get to products. Okay, this reaction is exothermic. We're starting here and we're getting energy out. Delta H reaction is we're exothermic, negative. Okay, so we're getting energy out. Okay. So that's activation energy of reaction, and we have these reaction coordinates. So here's a reaction coordinate of a similar type of reaction. Okay, we have well, this is acetaldehyde, again producing methane and CO. Okay, and the activation energy in the forward direction, we have this magenta reaction coordinate, and the activation energy in the forward direction is 198 kilojoules per mole. Okay, if we add some iodine as a catalyst, though, the activation energy drops by 64 kilojoules per mole to 134. Okay, so it's a modest reduction in the barrier. You know, it drops to there, but actually there's a massive increase in rate. So the rate increases by 20,000 times. Okay, why? Okay, and again, I'm using the same equation. We have the rate constant, K is equal to A exp minus EA over RT. Okay, so K is equal to the exponent of minus 64,000 all over R times 773. Okay, And when you calculate that, it's 1 over 21,000. Okay, something like that. Okay, so that's the effect of a decrease or an activation energy barrier of 64 kilojoules per mole at 773 Kelvin. Okay, it affects you by 21,000. Okay, either increase or decrease. Okay. So, but why don't you calculate that also? Say you do it at 1773. Okay, 1,000 Kelvin higher. The effect of that energy barrier will be a lot less because it's exponentially dependent on the activation energy as a function of temperature. Okay, so it'll be a lot less at a higher temperature. So just calculate that, you'd be surprised. Okay, so the bond association and CC bond, we saw it there for ethane, it was 368 kilojoules per mole. Here it's about 340. For CH, 420. But the bond association energy for iodine-iodine breaking is just 153. So what's happening here is the iodine, you put iodine in, you get iodine radical, I radicals. And those radicals then can abstract a hydrogen atom, initiating the process. And that initiation lowers the energy barrier of the overall process by 64 kilojoules per mole. Okay? And that's why it happens. Okay, so one last thing. We can also get thermochemistry from kinetics sometimes. Okay? So say we have this reaction. I mentioned it earlier. We have ethane giving us 2 methyl radicals. And the activation energy is 368 kilojoules per mole. Okay? Or delta H reaction, sorry, is 368. So we know that the bond association energy is 368 kilojoules per mole. Also, remember always that radical-radical recombination reactions, they don't have an activation energy associated with them. Okay? Radical-radical recombination, 0 activation energy typically. Okay? So delta H reaction is E forward at minus E reverse. E forward is 368. E reverse is 0. So delta H reaction is 368 kilojoules per mole. So, and we know that delta H reaction is 2 times the heat of formation of a methyl radical minus the heat of formation of ethane. That's the reaction. Okay? So the heat of reaction then of a methyl radical is going to be delta H reaction plus the heat of formation of ethane all divided by 2. Okay? But the heat of formation of ethane, I think, did we say minus 84? I've changed it now to minus 85. Okay? Don't shoot me. Okay? It's minus 85 kilojoules per mole. So the heat of formation of a methyl radical is 368 minus 85 divided by 2 is 141.5 kilojoules per mole. Okay? So and remember, again, that's the BDE. It's the delta H reaction here is the BDE. It's the energy of the bond breaking. So we can, in this way, get tables of bond association energies also, if we can measure the heats of reaction of these types of reactions. So if we want to get the BDE of a CH, we try and get ethyl plus H. Okay? But you can see here, we can get the heat of formation of a methyl radical. So we don't have to try and call Sigma Aldrich and ask them for methyl radicals so that we can put them into the bomb calorimeter. There's ways that we can get the heats of formation of these things. Okay. Okay, so the common mathematical functions, you've got kinetics, we've got the Arrhenius expression, but it's similar in vapor pressure with the Clausius-Clapeyron equation. P is equal to P infinity e to the minus delta H of vaporization all over RT. And in viscosity, you have the Andrad formula where you have eta is equal to AE to the plus E over RT. But if you look at the inverse, you have fluidity is fluidity infinity times the exponent of minus E all over RT. They're all Arrhenius type equations. They all have this activation energy, exponential dependence on activation energy and temperature, inverse temperature. Okay, so that's Arrhenius equation. Okay, now I'm going to switch gears a little bit and talk about simple collision theory. Okay, and just a little bit on that. Okay, so, sorry. So say we have this reaction, I don't know, H plus O2 gives O plus OH, okay? Just something like that. Okay, H plus O2. So here we have the reactions coming in. There's an energy barrier for transition. We have to break this OO bond and generate the HO bond, okay? And then we relax the product, so we've got O plus OH, something like that, okay? If that was true, then these should be the same color. But anyway, it doesn't matter what it is, okay? So the question is, what is the best geometry of approach for the reactants, okay? What is the most efficient way of supplying energy to overcome the barrier? And what is the rate of movement along the coordinate to produce the products? Okay. How is the energy distributed among the products of reaction? Okay. How do we do all these? So we go back, and actually, this is where I saw this picture. So if you go to Wikipedia and you Google simple collision theory, you see this picture, okay? So again, we have low concentration, few collisions, high concentration, more collisions. So but for simple collision theory, we assume the molecules are hard, structureless spheres like billiard balls, okay? So you assume there's no interaction between them until they come into contact with one another, okay? So there's no like forces of attraction or anything, and that they are impenetrable. They maintain their size and shape, and they cannot come closer than their radii, okay? And if we assume that, then we can picture a situation something like this for their collision, okay? So here we have species A colliding with species B, okay? So if we assume that the molecules are hard spheres, and we assume that every collision is reactive, okay, then if we calculate the rate of collision, we calculate the rate of reaction, okay? And that's simple collision theory in a nutshell, okay? So if in 1 second then, a typical A travels the distance is equal to the velocity of A times t, okay? So this is an A now in a big bath of B, okay? So, and the A's will collide with all B's within collision cylinder of volume pi RA plus RB squared times nu A. Okay, so here in 1 second. Okay, so remember the distance is equal to the velocity times time. Okay, so the distance that it's going to travel, if it's whatever velocity it has, in 1 second, the distance is equal to v nu, in other words. Okay, in 1 second. So there'll be the number of moles of B times pi RA plus RB squared times nu A will be a single collision of A with B per second. And that's the collision frequency, ZA. Okay. Okay. So the total collision rate, okay, of all A's in a mixture of of all A's and B's in a mixture of A's and B's will be the number of moles of A times the number of moles of B times pi RA plus RB squared times nu AB. Okay? And that's per meter cubed per second. Okay? And that's your collision frequency. Okay. So, but we know reaction rate is equal to the rate constant times the number of moles of A times the number of moles of B. I'll be coming back to this a little bit later, but just bear with me for now, okay? It's not, what I'm trying to say is, this is actually more correct, I should say. You should actually be talking about moles of species, not concentration, okay? So it's number of moles of A times number of moles of B. I'm going to come back to this a little bit later today, probably, okay? So the collision rate then is equal to, or we know the collision rate is equal to pi RA plus RB squared times nu AB times the number of moles of A times the number of moles of B. Well, if that's true, then we know that K2 then is equal to pi RA plus RB squared times nu AB. Okay, the rate constant is equal to this portion here. And that's equal to the collision cross-section, sigma AB times nu AB. Okay, so where do we get nu AB from? Okay, well, it comes from the Maxwell-Boltzmann distribution of velocity. Nu AB, the collision rate of A with B, or nu AB, is equal to 8 kT over pi mu, well, the square root of 8 kT over pi mu. Okay, this is on a molecular level. If you want to express it on a molar level, you can say it's the square root of 8 RT over pi mu. Okay? Where mu is, so we have 8, that's Boltzmann's constant, times T, all over pi, times mu, which is the reduced mass. So it's the mass of A times the mass of B, all over the mass of A plus the mass of B. So the cross-section, sigma AB, is pi RA plus RB squared. Okay. So we have, in practical units, nu AB is equal to this constant. We take out the constants, times T, times the relative molecular mass of A plus relative molecular mass of B, all over the relative molecular mass of A times the relative molecular mass of B. Okay, all to the power of a half, where this is in kilograms per mole. Okay, so here's a little problem. Okay, let's try and explain it a little bit better. Okay, calculate the mean time between collisions experienced by a single argon atom at 300 Kelvin and atmospheric pressure. The collision diameter for argon is 0.29 nanometers, and the relative molecular mass of argon is 0.04 kilograms per mole. Okay, so the collision cross-section is pi r squared, pi d squared, RA plus RB squared, which is d squared, which is 2.64 times 10 to the minus 19 meters squared. Nu AA is 563.67 meters per second, which is twice the speed of sound. Okay, it's just saying, look, these guys are whizzing. Okay, they're not hanging around. Okay, okay, and we know PV is equal to nRT. So the number of moles of argon then is equal to number of moles per unit volume, which is P over RT, which is 101,325 over 8.314 times 300. Okay, so the number of moles of A is 40.1 moles per meter cubed, and that comes out to be 2.4 times 10 to the 25 molecules per meter cubed. Okay, so we have ZAA then is equal to the number of moles of A times sigma AA times nu AA. Okay, and that comes out to be 3.57 times 10 to the 9 molecules per second. So the mean time per collision is 1 over that, and that comes out to be 280 picoseconds. Okay, so the mean time between collisions just at 300 Kelvin is actually a very short time. Okay, 280 picoseconds. Okay, so here's a test of simple collision theory. I do out the numbers here, and I show you, but please do them yourself, right? Take the values, put them into the equation, do the calculation, just to see that you can prove to yourself that you can do it, and check the numbers as well, that I haven't messed it up, okay? But here you have methyl plus methyl giving us ethane, okay? And what is the rate of this reaction using simple collision theory? At 300 Kelvin, okay, the relative molecular mass of a methyl radical is 0.015 kilograms per mole, and the collision diameter across is 0.308 nanometers. Okay, so the rate constant is sigma AA times nu AA, which is 2.98 times 10 to the minus 19 times 920.25. So just work out this. So this nu AA is the square root of 8 RT all over pi mu. Okay, so that comes out to be 920.25. Sigma comes out to be 2.98 times 10 to the minus 19. Okay, when you work that out, the rate constant is 2.745 times 10 to the minus 16 meters cubed per molecule per second.
What was mu again?
Yeah, it's the square root of 8 RT over pi mu. on a per mole, on a molar basis. Okay? So if we convert this into something that I'm more used to, which is centimeters cubed per mole per second, that comes out to be 1.65 times 10 to the 14. Okay? For the rate of collision. Experimentally, it's measured to be 2.4 times 10 to the 13. Okay? So what we calculate is nearly an order of magnitude higher. Okay? Not quite. But actually, that's a good result. Okay? Usually, the calculation is way, way bigger than the experiment. Okay? Sometimes the calculations can be smaller. I was looking. A good place to look at this, actually, is Chemical Kinetics by Seekins and Pilling and Seekins. So Mike Pilling and Paul Seekins. Mike Pilling sometimes gives the lectures here. Okay? So there's a book of Chemical Kinetics by Pilling and Seekins, Pilling and Seekins. And they talk about simple collision theory in there. So it's a good place to look at this. Okay? But usually, the calculation is bigger and sometimes mostly way, way bigger than what you measure experimentally. So the temperature dependence is all wrong. Okay? So what are we missing? And of course, we're missing an activation energy. Okay? We're assuming there's collision, it either happens or it doesn't. Okay? And what we've been assuming is that every collision is reactive. Okay? And we've got to relax that assumption, because not every collision is reactive. Okay? So we can improve it by saying, okay, we have this critical energy, below which the reaction doesn't happen, and above which it does. And again, it's an all or nothing sort of thing. It either happens if it's above it, or it doesn't happen if it's below it. You know, it's all or nothing. Okay? So then what fraction of collisions have an energy greater than the collision energy? And that again comes from Maxwell-Boltzmann. So you have this frequency is equal to the exponent of minus a critical energy all over kT, according to Maxwell-Boltzmann. Okay? So that's equal to, this is on a molecular level. On a molar level, it's equal to minus EC all over RT. Okay? So now we have the rate constant is equal to sigma AB, nu AB, times the exponent of minus EC over RT from simple collision theory. Okay? And now, so this is our A e to the minus EA over RT. And everything is perfect. Okay? So simple collision theory and Arrhenius are the same. Okay? Well, they're not. Okay? They're not quite. They're very similar, but they're not quite the same. Okay? So what I'm saying is that the critical energy is not the activation energy. Okay? So if we look at it, if we compare with Arrhenius, we have rate constant is equal to A e to the minus EA over RT. And we just derived that this K2 is equal to sigma AB, A to RT over pi mu all to the power of a half, times the exponent of minus EC over RT. Okay, on a molar level. Okay? So the question then is, right, okay, so that you can relate all of this to the A. So is EC equal to EA? Question. And the answer is no. Right? So why not? So first of all, if we look here, the d log k all over d1 over t, okay? So the differential of log k with respect to 1 over t is equal to minus EA over R. Okay? So the differential of this with respect to 1 over t is minus EA over R. And then we have this from here. We have the rate constant is equal to this expression. And so we can say, okay, if we just take out the constants, we can say it's equal to y, just put all the numbers in there, times t to the half, times the exponent of minus EC over RT. Okay? Don't worry what y is. It's just a constant. Okay? And then we have log k is equal to half log t minus EC over RT plus log y. Okay? So we're just getting the log of that. Okay? And then we have log k is equal to minus a half times log 1 over t. Okay? Is that okay with everybody? Okay? Minus EC over R times 1 over t plus log y. Okay? So then we have d log k all over the differential of log k with respect to 1 over t is equal to minus a half times t minus EC over R. Okay? And that's equal to, we had up here, that's equal to minus EA over R. Okay? So when you have this, you can see that EC is equal to EA minus RT all over 2. Okay? So we actually have then K2 is equal to sigma AB, nu AB, times the exponent of minus EC over RT, and that's equal to sigma AB, nu AB, times the exponent of minus EA over RT, if you want, times e to the power of a half. Okay? So there's a little bit of a difference between the EC and EA. Okay? I think that's nice. It just shows you the difference. Okay? But if I go back, I don't really talk about it here, and I hope I can remember the expression. Is it called a steric factor? Is that right? Okay, so they say, okay, the reason that the calculated and the experimental value differ is because of the steric factor. And here, the steric factor would be about 0.12 or something like that. Okay, so if you multiply 0.16 times 10 to the 14 times whatever it is, you'll get 2.4 times 10 to the 13. That might be 0.12 or something. I don't know, whatever it is. Okay? So that's your steric factor. I call it the fiddle factor. Okay? Your fiddle factor to get the calculation to agree with the experiment. Okay? Okay, so that's simple collision theory. Okay, so now I've sort of finished with the theories. I'm not going to go into any other ones. I'm going to talk about using different facilities for measuring reactions. Okay, so we have jet-stirred reactors and flow reactors. Okay, so let me do these, and then we'll take a break again. Okay? Okay, so here's, this slide I got from Philippe de Gaulle. It's very nice. Okay, and so this is a jet-stirred reactor here. So we have an inflow of our fuel coming in. We have an atomizer and a vaporizer. So we have inflow of fuel and oxygen coming in here. Okay, the system is heated. Here we have coils for heating, and it comes into the flow reactor, or sorry, jet-stirred reactor in here. And this is a close-up of it here. Okay, so this is the inlet. We've got 4 jets all at right angles to one another so that your mixture is very well mixed inside the reactor. Okay, and then you've got a thermocouple here to measure the temperature, and you have a probe, a sampling probe, which goes to maybe GCMS or FTIR or whatever it is to measure the species from the reactor. Okay, for analysis. So there's one thing I always ask. So this is fused silica. So this is what it looks like in real life. It's glass, right? Ultimately, okay, glass. And here's the jets. Okay, so they're at right angles so that the gas gets very well mixed very quickly inside the reactor. Okay, and you can have the thing coming out here. So if we go back here, if we just look, why is this quartz then inside this metal tubing? Okay, and the reason is that Philippe can do experiments at likes to do experiments at 10, 12 atmospheres, higher pressure, okay? And so if we just had 10 or 12 atmospheres of gas flowing in here, right, and it was open to the atmosphere, you'd take your eyes out, exploding the silica tube, okay? So what he does is he puts it inside this metal tube, he equilibrates the pressure between the quartz and inside the metal tube, and he can do experiments at 12 atmospheres, okay? So a nice thing, that's why it's set up like that, okay? And then we have the heating system there, okay? So that's how and here's some data. It's not from Philippe's thing, but it's actually from Frederic Badin-Leclerc's group, okay? It's taken for N-heptane, it's N-heptane data, taken at an equivalence ratio of 1, with a constant resonance time inside the reactor of 2 seconds at atmospheric pressure with 0.5% fuel. The reason we have 0.5% fuel, or you don't want too much heat release. Keep it pretty isothermal, okay? And here's oxygen profile. So there's, I don't know, 25 experiments or something provided here. So each point here is an analysis of the gas coming out of the jet stirred reactor, okay, that experiences these conditions. So you can get a very wide range of species profiles as a function of temperature, okay, at this constant time, okay? So here's oxygen, here's the fuel, you've got carbon monoxide and water there. Here you've got some olefins, ethylene, methane, propene. Here's some small oxygenated species, cyclic ethers, all sorts of different compounds, okay, reported. A very rich data set that can be used then to validate a model. And we'll be talking about that. Yeah.
How is the chamber flow?
No, it's constant flow rate. So you've got, and I'll be talking about that in a minute. Okay, so so it's constant flow rate. So you know the volume of the reactor, you know your volume flow rate, so then you can measure the time. I'll be talking about that in a minute. But this is just showing you the rich data that you can get. And then the lines here are a model prediction of those data. Okay, so we can describe what happens here. Okay, so first of all, let me go back. And I alluded to this a minute ago when I was talking about simple collision theory. And I said, look, it's the number of moles of A times the number of moles of B. It's not concentration of A times the concentration of B. And the proper definition of rate of reaction is actually 1 over the stoichiometric coefficient times the change in number of moles of a species with respect to time, not change in concentration. Okay? So it's moles per second, actually, is the proper definition. Okay? And it's positive for products and negative for reactants. So example, if we have 2 moles of H2 plus a mole of O2 giving us 2 water molecules, stoichiometric coefficient of H2 is -2, that of O2 is -1, and water is +2. Okay. So at constant, if we look at it though, at constant volume, we know the concentration is number of moles per unit volume, or number of moles is equal to volume times concentration. Okay? So the change in number of moles of A with respect to time is the volume times the change in concentration with respect to time. So the old rate of reaction was the rate of reaction per unit volume. We're assuming that the volume was 1, always. Okay? So that was just keeping it simple. Okay? So we're assuming the volume was 1. So the change in concentration with respect to time is 1 over volume times the change in number of moles with respect to time. So just to bear that in mind. Okay? So just, if we know that, we can move on. Okay. So I'm going to skip over this slide, and we'll go to our stirred reactor. Okay? So here we have the jet stirred reactor. It goes to the question you were asking now, right? So we have gas coming in. It's not quite depicted like this. I showed you the picture a minute ago, okay? But here we have gas coming in. The reactor has a certain volume, and then we have the gas coming out. Okay? So if we look at reaction then, the inflow should be equal to the outflow plus whatever reaction we have. But we know the change in the number of moles of A with respect to time is equal to the rate constant times the number of moles of A. And that's equal to the rate constant times the volume times the concentration of A. Okay? Okay, so going back to the inflow is equal to outflow plus the reaction. We have then the inflow, which is the volume flow rate times the concentration of A at the inlet, is equal to the volume flow rate times the concentration of A at the outlet, minus the change plus reaction, which is the change in the number of moles of A with respect to time, which is minus dNA dt. Okay? So the volume flow rate times the concentration of A at the inlet is equal to the volume flow rate times the concentration of A at the outlet, plus K times V times the concentration of A at the outlet. Okay? And we just rearrange this equation. I put it in. I used to have it in one step. I put it now in 3 steps. So it's baby steps, so we do it straight. And what we see is, look, the concentration of A at the outlet is equal to concentration of A at the inlet divided by 1 plus K times V all over nu. But what is V all over nu? What's V? Is the volume. And what's nu? Volume flow rate. So it's going to be volume per unit time. So volume divided by volume per unit time is what? Time. T. So this is actually the concentration of A at the outlet is equal to concentration of A at the inlet divided by 1 plus KT, ultimately. Okay? So typically, Philippe will not give the volume flow rate and the volume of his reactor. He gives time. Okay? So he knows the volume of the reactor. He'll measure the volume flow rate, and he'll convert that into a time. So you don't provide that. Okay? So how would you test that this is true? How you test this is true is you vary the volume flow rate, you measure the concentration of A at the outlet, the concentration of A at the inlet, and the rate constant should be the same if your reactor is behaving well, ideally. Okay? And that's what Philippe did to test his reactor. Okay?
This can be
also you typically what people, you can measure it at different pressures. So you, like everything else, you can keep 2 parameters constant, changing the third. You know, so typically though, what he'll do, well, he'll do something probably at atmospheric pressure, for instance, and then he'll measure species either as a function of temperature, keeping the time constant, or as a function of time, keeping the temperature constant. Okay. Okay. And then he can up the pressure to 10 atmospheres and do the same. And then you can compare the 1 atmosphere and the 10 atmosphere results. Okay? So that's a jet-stirred reactor. Here's a picture actually of a variable pressure flow reactor I have at Princeton University. Actually, it's not here anymore. It's in University of South Carolina. Okay? Professor Dreyer has moved there. Okay? And it hasn't been reinstalled there. But there's just something a little bit different about this. Again, you've got the fuel inlet, you've got a mixing region here, and now here's the injector where your fuel-air mixture are mixed. Okay? And now your fuel-air mixture can flow down the reactor. So it's this cylindrical tube that is flowing down. Okay? So in this configuration, you've got the inlet here. Your gases are now mixed and they can react. And then you have a probe here. And you can move this probe. So if you think about it, look, If we move the probe all the way up to there, how long? Again, you can work out the volume. You've got a volume flow rate, so you have a time. Okay? So what is the time? If I have the probe right up next to the inlet, how much time do you have for a reaction? Virtually none. Okay? So the way this is operated is you have a typical operating volume flow rate. You know the volume in the reactor. And then you'd have different positions for the probe so that they would be different times in the reactor. Okay? And the longest time would be when the probe is right next to the outlet here at the very end of the reactor, and the shortest time is right up where it's at the inlet. Okay? And you've got different points along. Okay? And that's typically what you would do, is measure different times. Now, you could actually keep the probe near the end, just leave it sit there, keep the flow pretty constant. It would have to vary a little bit with temperature, okay? Because as the temperature varies, the volume flow rate is going to be affected by that, right? But you can then keep time constant and measure as a function of temperature, for instance, in the reactor. So you can do different things, okay? You can sit at a constant temperature, measure species as a function of time, or keep the time constant, measure species as a function of temperature, okay? And then you can up the pressure and do different pressures as well, okay? So that's how it works. But what about the kinetics inside it? Okay, how do we calculate them? Okay, it's all very complicated. I wish I had this in maybe stages, but anyway, it's not. Okay, so again, we have the same equation. Okay, the change in number of moles of A with respect to time is equal to the rate constant times the number of moles of A, and that's equal to the rate constant times the volume times the concentration of A, right? So we have, again, inflow is equal to outflow plus reaction. So the inflow is the volume flow rate times the concentration of A at the inlet, and this is equal to the outflow, which is equal to the volume flow rate times the concentration of A plus the change in the concentration of A, okay, minus plus reaction, which is the change in number of moles of A with respect to time. Okay. Now, let me just, here I have A at the inlet and A at outlet. And here we have the cylindrical reactor of a certain volume. And what we're going to do is now look at an infinitesimal, okay, small change in volume of the reactor, okay? And so we have the volume nu times the concentration of A is equal to nu times concentration of A plus nu dA, the change in the concentration of A inside that volume, okay, minus the change in number of moles of A with respect to time, okay? And I just expanded this, basically, okay? So this and this are going to cancel, and we have minus nu, this infinitesimal small change in the concentration of A is equal to minus the change in number of moles of A with respect to time, okay? So, but now we have minus nu delta A is equal to K delta V times A, where these are infinitesimal small changes in concentration and volume as you travel down the reactor, okay? So if we integrate that then and just reorder the equation, okay, we have the integral of the change in the concentration of A over the concentration of A is equal to minus K all over nu, the integral of delta V, okay? So at the inlet, we have the concentration of A at the inlet, and here we have the concentration of A at the outlet. So if we integrate from the concentration of A at the inlet to the concentration of A at the outlet, the change in concentration of A over the concentration of A, and that's equal to minus K all over nu, the integral from 0 to V dV, okay, through the reactor, okay? So then we have log of the concentration of A at the outlet minus the log of concentration of A at the inlet is equal to minus K times V all over nu, okay? And again, what is V all over nu? T, Okay? So actually, it's actually first-order kinetics that you're really looking at. You have log of concentration of A at the outlet is equal to log concentration of A at the inlet minus K times T. Okay? So again, when Professor Dreyer provides data, he doesn't provide the volume and the volume flow rate, he converts that to time. Okay? And it's time that's provided. Okay? So that's the kinetics inside a flow reactor. Okay? And this would be a standard. So this is actually where the probe isn't moving. Okay? So the probe position is kept constant. The volume flow rate will be varied slightly because you're ranging in temperature from 500 to 800 Kelvin. Okay? And here we measured, this is from a paper that we published together. It's actually nearly 20 years ago now, I'm ashamed to say. Okay? So here we have oxygen dimethyl ether. And I'll be showing you this actually later in the week. Okay? And you can see characteristic negative temperature coefficient behavior for this fuel. And the lines, again, are the model predictions. But what's the point of this? Okay? It's just showing you the kind of data that you can get from the reactor. Okay? And each one of these points is an experiment. Okay? Where all the things. So again, there's maybe 20 or 25 experiments performed here in this, from what's plotted here. Okay? So the temperature, you're sitting at the point, you've got the flow rate, you're measuring the species in that time. Okay? Probe being kept constant. Okay? You up the temperature, the rate at which the gas is going to flow is going to be a bit faster, so you're going to have to lower it a little bit going in so that the volume flow rate, the time is constant. Okay? So, okay. And I think that's a good place. Let's take a break. Okay? And we'll talk about shock tubes and RCMs next.